Right, so first of all, I've got a confession to make. I thought I was going to be talking for an hour, and I found out I'm going to be talking for around about 35 minutes, so this is going to be fun. I have a demo right at the end. I can either talk really fast so I can get to the demo of a multi-agent app, or I can talk slowly and I can just give you the link and you can do the demo on your own. Who wants me to talk fast and then get to the demo? Hands up. Yeah, ooh, okay, woo. This is going to be fun then. Okay. All right, so a little agenda. I'm going to give an intro to AI apps and GenAI in a kind of fun and unusual way. I'm going to give an intro to vector embeddings and RAG. Might skip over that if enough of you already know about that. I'm going to talk a fair bit about performance at scale in Azure Cosmos DB. Just show of hands, how many people have used Azure Cosmos DB? How many of you have heard of Azure Cosmos DB? Right, okay. You've all used it because I presume you all use ChatGPT. Everybody use ChatGPT? Yeah, yeah. ChatGPT uses Cosmos DB, so you all use it. Okay, I'm going to talk about vector search, full text search, hybrid search in Cosmos DB, and the general umbrella of semantic search. I'll give an intro to agents and why multi-agents and so on. And then I'm going to dip my toes, hopefully if I get there, in LangGraph and a demo of a multi-agent app that we've built in our team, and we've done various workshops and hands-on labs with this, and it uses OpenAI and LangGraph and Cosmos DB to store chat memory and vectors and transactional data as well. All right, so intro to AI apps and GenAI. What do I mean by AI apps? Obviously, I mean large language models. That's the state of the art. That's where the technology is right now, GPTs and so on. Of course, over at Microsoft, we generally tend to favor OpenAI, but as I'm sure you all know, there are various derivatives of these models. Rather than me go through every sort of pattern and technique, I thought it would be interesting to just take a step back and ask the question, why are they all important? If the answer to that doesn't immediately spring to your mind, then hopefully the next few minutes will be interesting. If not, then you can switch off and go to sleep for the next few minutes. But I'm going to give you a controversial statement that was made on social media by my old colleague, Tim Scarf. Anybody heard of Tim Scarf? Anybody watched Machine Learning Street Talk? One of you, only one of you. It's the most subscribed YouTube channel for machine learning, highly recommended. Tim came out with this about 18 months ago, so pretty early on into the whole LLM thing. He said, LLMs perform diffused information retrieval given a prompt. They are basically databases, indeed a new form of database. So you can imagine why this was music to my ears as somebody who works on a database. Of course, he got a massive spectrum of different reactions to this. On the one end of the spectrum, people saying, what are you talking about? LLMs are so much more than this. This is AGI, this is Skynet, this is, the technological singularity. And then the other end of the spectrum, people were saying, well, yeah, I don't even think they're as good as databases. So it's fair to say it was fairly controversial. It doesn't really matter what you think about this statement. It kind of serves for my analogy. And when I get to the end of this, you'll say, yeah, okay, that was obvious, but sometimes it's good to bring things from the back of your mind to the front of your mind. So if we run with Dr. Scarf's statement, let's compare the old database with the new database. What do traditional databases require? Of course, they require highly structured and rigid query languages as input, usually SQL or some derivative. And for that, you get 100% accurate deterministic outputs. What does the new type of database require? Highly flexible input. Of course, it's human language. We've all seen how impressive this is. But you don't get 100% accurate and deterministic outputs, but it's often very close. And of course, this is what's impressive. We all know about this by now. And the fine-tuning of output accuracy and predictability is really one of the primary goals of all these patterns. So if you're new to these patterns for building GenAI apps, really what we're talking about is a trade-off between input flexibility versus output accuracy and predictability, and ultimately how much code you write as a developer if you're building these kinds of experiences versus letting the LLM do all the work. And that may be a scary statement to make if you're a developer. Is AI going to take my job and that kind of thing? My own 2 cents of this is, there's always paradigm shifts in technology. The goalposts move and we just have to move with the times and so on. But all of these developer patterns are driving at the same thing. I'm not going to go through each of them because I won't have time, but essentially, if I take the first one as an example, tool use or function calling, of course, that's where you get the LLM you annotate a particular piece of code that you have written, that you know what the behavior is, you know it's deterministic, you annotate it as a tool that can be called by your LLM, it doesn't actually get called, the LLM returns a schema, and then the framework knows how to call that particular function. And what are you doing here? You're making your end-to-end application more deterministic, more predictable. You're not relying on the LLM to do everything and generate its own code, which is perfectly capable of doing, and it could generate garbage. You're just saying, get me the context and get me the parameters that are required to call this function, and everything else is deterministic. And pretty much all of the other patterns are driving at the same thing. Let's be honest, we're trying to stop the LLM from hallucinating and making mistakes. So anyway, that's that out of the way. Intro to vector embeddings. Hands up if you're already an expert on retrieval-augmented generation. 1, 2, 3, 4, 5. Okay, not a majority. Okay, retrieval-augmented generation, 60 seconds. Here we go. So I like to call this spoon-feeding the LLM. Instead of the LLM relying on its own internal training data set to give you the answer that it wants, which could include information that's wrong, or it could just not be there because it's not available on the internet. Or whatever it's been trained on. Instead, you're providing your own information. So typically, you'll have some documents that will contain text. You'll divide these documents into chunks. You'll call some kind of embedding model that will then convert that text format into numerical format, arrays of floating point numbers. You'll store that in a vector store like Cosmos DB. Question comes in text format. That's going to be converted into exactly the same numerical format. The application is going to call your vector store using some kind of numerical distance algorithm like cosine similarity or Euclidean distance, which turns out to be a good proxy for semantic similarity. You get a rank-ordered result of chunks of data that are similar to the question that's being asked. The application then responds, or doesn't respond, sorry. It takes that as context and says, okay, here LLM, this is the information that I want you to use to form the response, and here's a prompt telling you how to do it. LLM responds, and you respond to your application. And you've done it in a way that it's more predictable because you've augmented the generation that the LLM would otherwise do based on its own internal reasoning, and it may make mistakes. And if you're clever, you'll also store that response in the vector store as well. And if the same question is asked in the future, you just retrieve the same response, provided there are no issues with data staleness. In that case, and this is of course a technique that we call semantic caching, which sits alongside retrieval augmented generation. So that was, I don't think that was quite a minute, but I think it was close. So that's RAG pattern. It's very popular, obviously. Most companies that are building these types of experiences are injecting their own data into the process. The big challenge that we see from the database side is, of course, ingesting the data into your data store. And I want to talk about an interesting use case that we're seeing emerge quite recently. It's becoming very popular, especially with people using Cosmos DB, but also databases that provide vector indexing and search capability alongside their operational transactional capability. And actually, most of the AI frameworks that are around today, so I'm thinking about things like LangGraph, LangChain, Spring AI, Llama Index, Semantic Kernel, and so on, they don't actually interpret this very well at this point in time. So most of them will provide an abstraction to your vector store of choice, whether it's Pinecone or Cosmos DB or MongoDB. And that abstractions, like any other abstraction, usually have two purposes. One is to make the code common regardless of which thing you're connecting to you're using, and the other is to reduce boilerplate code. But what most of the abstractions don't recognize is the fact that you could be using your vector store as something other than a vector store. They assume that you're just using it as a vector store and you don't actually want to store your transactional data and your vectors together. What we're seeing is more customers wanting to do that. And so using these frameworks is maybe not ideal at this point in time for that particular scenario. So I have a little demo here. And what's going on in this scenario is, anybody use Azure Cloud here? Okay, a few of you. Anybody heard of Azure Functions? Okay, so this Azure Functions is a serverless technology. Serverless meaning you just call it, and then when you don't call it, it's not consuming any resources, it's not charging you anything. This is an Azure Functions piece of code written in Python that is consuming something called the change feed in Cosmos DB. This is a distributed log store that allows you to consume changes that are happening on a particular container in Cosmos DB. It's, you know, everything around scaling behind the scenes is completely transparent. It uses a change feed processor to read changes across multiple partitions and so on. You just have this simple piece of boilerplate code. All that's going to do is listen for changes in a particular container that contains some operational data. So customer, the application is storing, let's say, a customer entity that contains information about a customer, but it also contains, let's say, customer notes, so notes about interactions with a customer. You can imagine like a claim scenario or something like that. Operator is storing some notes, and that's changing all the time. It's an operational database, and so that's always being updated. But they also want an AI assistant to be able to reason over that text as well. You don't want to have those two bits of data stored in different stores. What's the point? You want it all together. So in this scenario, what's happening is every time this data is stored in Cosmos DB, we've defined customer notes as the field that is going to be embedded. The function is going to read from the change feed. Every time a change happens in the operational data store, it's going to call an embedding API. It's going to embed that data and then write the vectors back into the same record. So yeah, and the JSON document is going to be converted into a dictionary, and then the embedded data is going to be written back to the record. So we've got the function starting up here. It's not a live demo. I recorded it yesterday, so it's just going a bit slower than I would like. So okay, function is starting up. It's just running locally in this scenario. And in VS Code, you've got this nice feature where you can edit records in Cosmos DB locally. So I'm just going to create a JSON record. I'm going to paste it in there. See, it has that customer notes field. I save it. Change feed picks up the change. Function is going to process that change, call the embedding API, transform it into a vector, and then write it back to Cosmos DB. And then you see when I refresh the document, the vector appears there. And this scenario is getting increasingly popular. Just treating vectors and transactions is the same thing. So if you want to try it out, this is a sample of the Azure Functions sample that will do this in Cosmos DB. The QR code will link to the same demo. And I guess the key takeaway here is you may want to store vectors and transactions together. In the early days of RAG, most of the vector stores were dedicated vector stores like Pinecone and so on, but we're seeing this use case increasingly so. All right, so performance at scale. Everybody okay? Everybody with me so far? Nothing, I'm not going too fast, okay? So of course, in case anybody doesn't know by now, and I already mentioned it before, OpenAI, of course, uses Cosmos DB to scale ChatGPT. All of the chat data that you're typing in furiously every day is stored in Cosmos DB. We've had to do an awful lot of changes. Needless to say, this is just a few of the changes we had to do on our Python SDK alone in the last 6 months. I'm not going to go through all of them because I don't have time, but I'll call out one of them, session token helpers. So that might sound very nebulous, but what this is about is threading the needle between consistency and availability in a distributed system. Who's heard of CAP theorem here? Quite a few of you, probably less than half of you. Okay, I'll probably have to go through it then, but that's what this is about, really threading that needle. It's very important if you're going to put your application into a database that is built for scale. I'm going to skip past a lot of these slides because basically it's just showing off about Cosmos DB and how we have SLAs and how we're able to achieve them with the architecture that we have. Long story short, we have hundreds of customers on each machine, thousands of customers on clusters of machines because we control resource governance at the software level. And the reason that we're able to do that is because we place circumscribed constraints on things like document size, partition size, vertical scale, and ultimately this means that Cosmos DB is a horizontally scalable database like most other NoSQL distributed databases. How many of you have experience of NoSQL distributed databases here? Okay, around about half of you. So for those of you who only worked with relational databases, the difference is instead of your data sitting on one machine, it's split up into multiple different machines for concurrency and high throughput and also unlimited storage capacity. But the challenge there is that you have to have some kind of partition key design or approach to be able to identify where your data is in the system. The advantage obviously is high scalability. Additionally, in Cosmos DB and systems similar to Cosmos DB, all of this data is replicated 4 times. in what we call a replica set. If those replica sets are stored on a region in Azure that it has availability zones enabled, they'll be distributed across those availability zones for fault tolerance. And if you have multiple regions, which we highly recommend in any distributed database for any application that is going to be deployed at scale, then those replicas are copied again into those additional regions, and then replication is going on either synchronously or asynchronously, depending on the consistency setting. And that's all very great, and it's all very seamless, and many of our customers rely on this capability that Cosmos DB provides. But it does mean that there are two very important decisions that you have to take if you're going to build anything with Cosmos DB, or to be frank, anything like Cosmos DB. You have to have a really good partition key design. You may have to have workarounds that involve multiple materialized views to be able to handle all of the different types of access patterns you have. In Cosmos DB, we have two ways of doing partitioning: regular partitioning and hierarchical partitioning, which allows you to have a parent key that effectively is a hash range, so child keys can occupy a certain value space beyond the size of a physical partition, so it gives you some flexibility. I'm not going to go into detail there. You can read the documentation. The other important thing is consistency choice, and I mentioned CAP theorem. There's also PAC-LC theorem as well. I'm going to go into that in a minute. So I mentioned sharing session tokens. This might seem nebulous, and it is. I wouldn't expect any of you necessarily to have to do this. This is actually something that we had to build for OpenAI, because they're a customer that really needs to thread the needle on consistency versus availability. But to do that and to talk about it, how am I doing for time? Not too bad. To talk about it, I have to talk about CAP theorem. Some of you know this already, but let's just go through it quickly. CAP theorem addresses data consistency in distributed systems. It states that only 2 of 3 properties can be guaranteed, and those properties are consistency, availability, and partition tolerance. That's what CAP stands for. In a nutshell, sort of really cut this short, in a scenario where you have an outage, let's say you have 2 nodes that are talking to each other and replicating to each other. If there's a network problem, so they can't talk to each other, or if one node is down, in other words, there is a network partition, you're going to favor either consistency in your system or availability. You cannot have both. It's not physically possible. Either you're going to say, I want my data to be consistent. I don't want there to be any chance of replicas having inconsistent data, so I'm going to return an error, which is an availability loss. Or you're going to say, no, I want my data to be, my application to return a response, even if that response is out of date at that particular time, and so you're favoring availability. And there are points along the spectrum, and Cosmos DB, like many other databases, offers different points along the spectrum, but they are trade-offs. There is no space where you can have both consistency and availability is the point I'm getting to here. So strong consistency in Cosmos DB would be obviously favoring consistency. All writes are synchronous to all replicas, and if any replica does not respond, then it's a failure. And then on the eventual consistency side, you're favoring availability. Of course, all bets are off. You could be getting a dirty read at any point in time, but you're always going to have availability because if a node is down, then you know your application will route to a different node. And 2 other concepts that are closely related, not exactly the same, but closely related: RPO and RTO. I imagine most of you have heard of this. Hands up if you haven't heard of it. Okay, so RPO, in plain English, how much data could I lose in an outage? And in RTO, in plain English, is how long will I be down in outage? If you want RPO 0, then you're going on the side of strong consistency within your distributed system. If you want RTO 0, then you're leaning towards eventual consistency. RPO 0 and RTO 0 are not both possible at the same time. The reason that I'm laboring this point and bringing this up is because it is very surprising to me how many customers we talk to do not realize this or do not want to accept it. I totally understand, right? Of course, we all want data to be consistent and available at the same time. We probably would all like to fly on a magic carpet to work in the morning as well, but it's not physically possible per CAP theorem. So there have to be trade-offs. In Cosmos DB, the default trade-off is something that we call session consistency. And so this is where strong consistency is only at the session level, meaning the client, the application that is connected to the database, it can read its own writes. In other words, monotonic reads and writes scoped to a partition range. So in other words, you're getting strong reads on all of the data that you write, but you're not paying the performance cost of having to guarantee strong reads on every single other client. So there's a compromise going on there. The pros of this, of course, it's a compromise, but if you have more than one client that needs a strong read on a particular piece of data, then obviously you have a challenge. And this is where OpenAI came to us and said, look, we don't want to set this at strong consistency or bounded staleness or quorum reads, but we don't want to have dirty reads on any of these clients. We need you to make it easier for us to be able to share session tokens around between different groups of clients that we have, because they had multiple agents that were doing various things on users' applications and reading their chat information and so on. And so they needed a consistent view on the data. Now, I'll admit this is more or less pseudocode. I wouldn't expect you to take pictures of this and go and implement this somewhere, but this is just to illustrate what they were doing. Typically they would create an item, they would use a previous session token that was stored in a cache. They would then get the session token from the create item that they've just done, which will be different coming back from the server. They add that to the cache, and then they use a convenience method that we had to add in the Python SDK to sort the latest token by looking at the LSN on the server to make sure that is actually the latest session token, so they can add that back to the cache, and every other client can do the same thing, and they're always reading the same view of the data. Don't get me wrong, this is very advanced. I wouldn't expect necessarily many of you or even any of you to be doing this kind of thing, but I'm just trying to make the point that if you really are struggling with wanting consistency in your system and availability, you have to look at each workload in granular detail and make trade-offs. At this level of scale, those are the kinds of challenges that you're going to run into. So key takeaway, RPO 0 and RTO 0 is not possible at the same time. You can get close. So I should mention here, recently Cosmos DB released something called per partition automatic failover. I don't have time to talk about it, but essentially this gives you RPO 0 with RTO of less than 2 minutes, which is very advanced. Most systems will not be able to do that. But again, it's not RTO 0 and RPO 0. This just isn't possible. Unless your application isn't doing anything. Obviously, if it's not doing anything, you're not going to lose any data and you're not going to have a downtime. But otherwise, if it's actually doing anything non-trivial, then you're going to be sacrificing somewhere. So balancing consistency with availability or latency is very important for large-scale apps. And partition key choice, of course, is also crucial as well. Oh, yeah, and I don't want to forget about data modeling. I don't have time to go into this, and I wouldn't have done anyway, even if I had more time. But alongside partitioning and making the right consistency choice, definitely, if you're coming from the relational database background, I should say, if those of you who are familiar with things like MongoDB, Cassandra, will know many of the same concepts will apply. But if you're coming from the relational world, many of the things that are best practices in that world are actually anti-patterns and vice versa in a NoSQL distributed database. So definitely worth checking out this video. It's only an hour and a half. It will tell you everything that you need to know if you're coming from the relational world. All right, so vectors, full text, and hybrid search. So how am I doing for time here? 22 minutes left. Have I got 22 minutes or 15 minutes? 15 minutes, okay. Right. So at Microsoft, we have a research-born algorithm called DiskANN for vector searches. This combines quantized vectors in memory with full vectors on SSDs with a graph structure. Long story short, the reason we've done this is to find the sweet spot between latency and recall. Recall being how accurate, how relevant your responses are when you're doing searches. And this is a difficult problem to get right, and DiskANN is very advanced in this respect. And there's a research paper that goes into a lot of detail about that there. I'm going to skip past some of these queries because in most cases they will be sort of common sense. You're just getting the vectors back based on some numerical input like I was explaining before. And you can filter, of course. Number one important thing to think about is isolating to a specific logical partition. If you're working with a distributed database and you're storing vectors at scale, you're going to need to think about a partition key strategy, just as you would do, frankly, with any application that is being built at scale. It's no different. with vector indexing as well. You can do cross-partition queries. It's not disallowed, but it is very it can get very expensive and it doesn't scale well. So I recommend thinking about partition key strategy. A couple of papers that will be very interesting, not papers, sorry, blogs, how we've achieved billions of vectors at scale with less than 100 milliseconds search latency. Not surprising that these recommend having a good partition key strategy, of course. And I should mention also as well, another blog on sharded disk gaining that we've just introduced recently. If you're already not familiar with partitioning, then this may be a little bit of overload, but basically it's the same thing, but sharding at the index level for vectors gives you an extra level, you could say, of hierarchy in terms of how you distribute the data within your vector store. So there's full text search and ranking support as well in Cosmos DB. Hybrid search queries are also supported. And we have something called reciprocal rank fusion, which combines the semantic similarity score with term frequency importance scoring as well. You may have seen this. And this can sometimes lead to more relevant results. I have a quick demo here. I'm just going to let it go and play here and just talk through what it's doing. So I just put a search input, which film does James Bond battle Spectre in, I meant to say. If you do just do a bog standard full text search with all keywords, it's going to return no results, of course. If you do any keywords, it might return some vaguely relevant results, but obviously it's not going to return the right results because I'm asking a question here that has multiple terms, and so you might think similarity search would do best here. But if I use full text search ranking here, I actually get results 1, 2, and 3 are the right results here. And if I remember rightly, when I used similarity search on this text, results 1, 2, and 4 are correct, but 3 is not. So it's not always the case that vector search is the best approach. And I think I did hybrid search as well in this demo. And I think that also gave me the right results as well, didn't it? Yes, it did. So the point being made here, if you want to try that app out, it's just this Streamlit Python app that connects to Cosmos DB and just does all the various different searches that it supports. I mean, ultimately, the takeaway here is vector search won't work for everything. So sometimes different approaches are necessary, or even multiple approaches side by side. So I think that's what I actually had linked here. So there's something that we call the OmniRag pattern. I don't know how many have heard this OmniRag pattern approach. Yeah, so this is the way, based on user intent, you might route to different types of store, not just different types of queries. Text search, hybrid search, semantic re-ranking, vector search are all different types of query, but you might route to actually a different type of store that structures the data differently, and those queries will have different benefits in different scenarios. So that's very advanced. I'm not saying that a majority of cases would fit that, but it's certainly we have a reference architecture. It's not a product. It's a reference architecture that happens to use Cosmos DB, and it's pretty interesting to look into. So, okay, how am I doing for time? 5 minutes, 10 minutes, 10 minutes? Okay. Intro to agents then. Let's see how quite quickly we can go through this. What are agents? So use AI to automate, execute business processes working alongside. Okay. So you've got a spectrum of things that agents will do, from simple retrieval on through doing tasks, being able to invoke functions, actually doing stuff, to being autonomous. I have to admit, I don't personally like the word agent to describe agents. And the reason is they're not agents, in my opinion. They don't have agency, but I can't articulate it as well as Dr. Scarf, so I'm going to let him do the job for me. What Tim said was the autonomy gap is where the magic fades. It quickly becomes obvious that LLMs have zero intelligence. There is no intelligence without autonomy. LLMs have no autonomy, therefore LLMs are not intelligent. When you turn an LLM into an agent, it diverges and decoheres exponentially fast. The only way you can prevent this mode collapse is by setting extremely tight operating constraints with careful prompting. So why multi-agent? My crude analogy for this, not nearly as eloquent as Tim, if I roll a dice, I've got a 1 in 6 chance, of course, of getting the number that I expect, the correct number. If I fix the dice to being 2 digits, then of course I have a 1 in 2 chance. It's a crude analogy, but the point I'm making is there are probabilities involved, there is randomness involved. These are stochastic algorithms. If you overload them with tasks, they're going to, as Tim says very eloquently, decohere exponentially fast. Specialized agents can handle distinct tasks, leading to more deterministic and accurate outcomes overall if you have multiple agents working together. What do most multi-agent frameworks have? They all have some form of agent encapsulation, from what I've seen anyway. What is the agent responsible for with prompts, and what tools can it call, and what other agents can it hand off to? They all have some kind of orchestration, how the LLM determines which agent to call next, which tool function the agent is going to invoke. State management, so this is passing through of messages, but not only that, it could be intermediate computations in between messages as well, and metadata, and anything basically that is occurring in the system. All of it is rich input into the LLM. It's not just about language interactions. Of course, as we've all seen, it can interpret code and metadata as well. And observability, obviously, pretty much every application framework will benefit from that. In this case, you want to be able to inspect the decisions made by the LLM end-to-end, because that's quite difficult. In fact, it's impossible for you to debug in your own code, obviously, so you need something that is going to introspect that. Statefulness here, I've already mentioned it. It's a superset of message history, but it includes intermediate computations and everything else that's going on in the system as a whole, and memory is a subset with short-term or long-term memory. I would say agents are a lot like intelligent functions or microservices. How many of you are familiar with microservices architecture? Most of you, all of you, yeah. So in my opinion, it's just my opinion, there's plenty of people that agree with me. I would almost call this agent microservices 2.0 or 3.0, or maybe even 5.0, depending on how big you think the paradigm shift is. But they all have inputs and outputs. They encapsulate logic. They're modular. They can be called repeatedly in different parts of an application. And they're composable. They can be chained or orchestrated with other functions as well. Who's heard of this guy? You may have heard of Satya Nadella. He came out with this comment recently. The approach we're taking at Microsoft acknowledged that traditional business or SaaS applications may fundamentally change in the agent era. These applications are essentially create, read, update, and delete databases with business logic. That sounds familiar. But in the future, this logic will migrate to AI agents. I think that that's true. I think that that's already happening, and maybe I won't go too much into that. How much time do I have left? 5 minutes? 6 minutes, right. I'm going to skip past all of this because it's just slides about LangGraph and try and get some of the demo done. That's the link to the sample if you want to try it out yourself, and I don't have time to show very much, which is almost certainly the case. All right, so let me go and just show, oh, I can't find my mouse here. What's happening? Oh. What is happening here? I knew I should have brought my Mac instead of my Surface. Task Manager. Okay. This isn't the app, by the way. This is just my laptop screwing up. Okay, well, you know what? I'm going to make an executive decision, and my laptop is screwing up, so I'm going to take questions. If you've got 5 minutes, happy to do that instead. The app is very easy to deploy. You just press, you type a few commands. If you've got enough access to Azure, it will deploy everything. And then it will also write the appropriate credentials to a local .m file if you choose the Python version, so that you can test it locally. You can also test it in the cloud, and you can go through everything. So, if I can get something to work here, yeah. Wow, this has not happened before. You know what? Let me just unplug this because it all started when. Okay, that's the reason. So if I plug it back in again, you should see it. Hello? Wow. Somebody doesn't like Microsoft over here. It's not showing up, so. Anyway, happy to share it with anybody that wants it. If you didn't manage to catch it, I'll see me afterwards. Any other questions?
Yeah. First of all, thank you very much for the presentation. Quick question. You indicated that it's possible with Cosmos, with this Cosmos approach to doing RAG, to have multiple strategies around how you do the search. So I think you indicated that you can do normal RAG.
Omni-RAG. Yeah.
Omni-RAG, and then I think you indicated full search.
Yeah.
Full
text search. Yeah.
Exactly. And then, as you know, there are other ways as well. So at times you might want to do the search based on both dense and sparse embeddings.
Yeah.
I just wondered, how would you do that typically, or I mean, have you done that yourself? Have you done this idea of hybridizing the way you do your search with the use of Cosmos?
Yeah, I mean, I haven't done it. I haven't done it myself, but that link, the last link that I pushed up there, if I can. Oh, is it displaying now? Okay. Let me just present from this slide. If I go back to this slide here, this is a reference architecture. It's not part of Cosmos DB. It's a solution accelerator that uses Cosmos DB and implements the kind of thing that you're talking about. So multiple different ways of searching, including sparse and dense data, but also different stores and basing it on user intent, which store you route to. And it uses the LLM actually to generate the code to write the queries to the different stores as well. So it's quite complex and convoluted approach. It's not something you could really, well, we didn't feel we could productize it in the database, but it's definitely a valid pattern. And for certain scenarios, it's the only approach you can take because you've got too many disparate types of questions that can be asked to be served by one type of search method, was the point I was making. Yeah. Hi.
Great talk, thanks. I love your analogy of LLMs being the databases. How should we think about truly transactional data? If you think about like sales, if an agent does a booking or a purchase transaction for the user, it would typically go to some sort of a Oracle or a Postgres database that backs a true SaaS application. So it's not even in a vector database. How do you integrate data between old school transactional DBs backing operational applications and all this new cool stuff with documents?
So I think the question, if I can repeat the question in my own language, you're saying, let's say you've got legacy heterogeneous architectures with different data spread in different places, and you want to find some way of reasoning over that using this RAG approach, right? I mean, I'll admit I'm quite sort of biased in my view that everything should just be put into Cosmos DB because we're building all the capabilities to do everything. But if I take my Microsoft Cosmos DB hat off, I guess where I would direct people to would be things like the dedicated stores or something like Azure AI Search, some store that makes it at least easy for you to pull data out of some source and index it in a store in that way is kind of designed for that approach. Cosmos DB isn't designed for that. It is an operational database that operates at very large scale and also supports vector searches. So the expectation is it's going to be a homogeneous architecture. You're going to do everything in Cosmos DB. Obviously, not everybody has that privilege or position. And then I probably would, if I was just forgetting about Cosmos DB, say, yeah, you want to use something that is able to be that glue. And there are platforms out there that sort of specialize in that. I wouldn't be an expert in them because I work on Cosmos DB. So. Hi.
I was wondering if you comment on the hybrid search capabilities with indexing on the vector column.
Yep.
Are there limitations? What about if hybrid structured data that you want to filter on has Together with indexing, this has caused challenges for me in the past. This is what I'm asking.
Yeah, so when you have many-to-many relationships, I guess, have you worked with a NoSQL database before? Or do you typically work with relational databases?
It was a relational database, yes.
Yeah.
And I was wondering if Cosmos might actually offer advantages in that.
Yes, yes, it does. And without giving a really long answer, essentially what you'll typically do in Cosmos DB, or something like Cosmos DB, typically is denormalization. So you'll materialize as much as possible in the record as you can. And even where you have many-to-many relationships that need to be updated or synchronized, you'll still materialize it in one record if you need to query all of that data. So a typical case would be like product tags and products catalog, and then you have a customer entity, and they'll both be sort of many-to-many relationships, because product tags can have relationships with many different products. Let's say you would have everything materialized in your products entity, but you'd also have the product tags and product category. When those update, you would use something like change feed to propagate that data back into your original entity. So for the steady state application, it's a slightly more complex approach than what you would do in a relational database. But then it makes that use case that you're talking about much more straightforward. You don't have to do joins and have to search for the data in multiple different places and having to be invoking vector indexes everywhere. It's all in one place typically, or at least within one partition, and filtering at that level. Everything else is always materialized in the same document typically. So this is one of the many reasons actually that NoSQL databases and document-oriented databases are a better fit for this scenario typically, and for GenAI apps as well, I would argue, because of the schemaless nature, but that's another topic. So, yeah.
We're at time.
Okay.
Thank you very much, Stephen.
Sure. Thanks.